Yeah, hello everyone. My name is Elijah Dalton. I am a grad student at the University of North Carolina, Wilmington. Thank you all for coming to my presentation on using Google Earth Engine and Earth observation data to create a green infrastructure suitability index for the Wilmington metropolitan area here in North Carolina. And this project is funded by NASA. Currently, there are 4.3 million homes in the United States that are susceptible to substantial flood risk, with the annual estimated loss in 2021 at $20.3 billion and an expected increase to $34 billion by 2050. So there is a clear need for open geospatial-based approaches and tools that better assess flood risk at community, local, and regional scales that provide implementable and sustainable solutions to managing and adapting to floods. And to further complicate planning efforts, sea level along the U.S. coastline is expected to rise on average 10 to 12 inches within the next 30 years, causing profound shifts in tide and storm surge heights, causing flooding to reach further inland. And by 2050, moderate, typically damaging flooding is expected to occur on average more than 10 times as often as it does today. So, assessing the vulnerability of critical coastal environmental resources to climate change exposure factors such as flooding allows for the identification of suitable management actions such as nature-based solutions. Nature-based solutions are solutions that are inspired and supported by nature to improve societal and ecosystem resiliency. An example of nature-based solutions include green infrastructure. Green infrastructure are hybridized infrastructure systems that use ecosystem services and traditional infrastructure systems to improve societal and ecosystem resiliency. And some applications include improved stormwater management, improved air quality, improved temperature quality, especially in urban areas where the urban heat island effect is prevalent, and the overall protection and restoration of our ecosystems. Now, the logic behind green infrastructure implementation focuses primarily on its multifunctionality. However, there are uncertainties around how, for whom, and to what extent green infrastructure can function. While the services that green infrastructure provides are often influenced by the design and density of the project, they usually only affect those within the immediate vicinity. So the spatial planning of green infrastructure directly influences the services it provides and who benefits. So for this project, my goal is to develop a cloud-computed, replicable, remote sensing and GIS-based green infrastructure suitability index using the U.S. Climate Resiliency Toolkit Exposure Sensitivity and Vulnerability Framework. I hypothesize that incorporating metrics of change into ecosystem dynamics derived from satellite data will enhance existing models of green infrastructure suitability. And for this project, I have three main objectives. First objective is to model flood and sea level rise exposure to derive a flood exposure index, and that is the exposure part of the toolkit framework. Second objective is to derive a vegetation type and condition index that goes along the sensitivity and vulnerability part of the framework. And objective 3 is to create a green infrastructure biophysical suitability index that also goes along with the sensitivity and vulnerability part of the framework, and so we can compute a final green infrastructure suitability index. And so my study area is the Wilmington metropolitan area, and so this encompasses New Hanover County, portions of Pender County, and portions of Brunswick County. And these are some of the towns that are also within this area. This is a map from the Wilmington Metropolitan Planning Organization. And this area contains multiple disadvantaged and environmental justice communities at recurrent risk from flooding. And this area is also extremely susceptible to hurricanes and tropical storms since it is on the east coast of North Carolina. So for the first objective, to estimate areas most exposed to flooding risks, I will be using freely available geospatial data sets at the county scale. I will use the FEMA National Flood Hazard Layers 100 and 500 year data set, the NOAA High Tide Flooding data set, and the NOAA 1 to 10 foot sea level rise data set, do a overlay analysis to get our flood and sea level rise exposure, which you can see to the figure on the right here. And this is just the modeled exposure where extreme susceptibility is in red, high susceptibility is in orange, medium is in yellow, and low is in green. And this is a slide. This is the same figure that I just showed you. This figure to the right shows the actual flood extent that occurred with Hurricane Matthew and Hurricane Florence within this area. And you can see basically all of the areas where flood susceptibility is extreme or high was reached during these hurricanes. So The second objective, to develop a vegetation type and condition index. For the condition or for the vegetation type part of this index, I'll be using Google Earth Engine machine learning algorithms to derive a land cover classification for 2020. These are the land cover classes that we'll be looking at, and we're mainly focusing on the wetland areas because these are the areas that provide the most ecosystem services, and they're also just good for flood mitigation and for filtering out pollution and other services as well. Now, Google Earth Engine is a cloud computing platform that I believe was developed around 2010. And it allows users to access and analyze vast amounts of geospatial data from satellites, aerial imageries, and other sources. And it is developed and maintained by Google, and it really just allows you to have access to imagery right at your fingertips with one line of code, and it makes the process so much more quicker to where instead of spending multiple days on a single classification, you can get it within minutes. Now for the vegetation condition part of this index, I'll be using a modified land trender workflow from this reference that's right here to detect areas experiencing significant positive or negative changes in vegetation condition and health. And land trender is a set of spectral temporal segmentation algorithms. So basically it takes Landsat images at the pixel level and is able to detect for this project 2000 to 2020 how pixels have changed spectrally and to determine whether vegetation has gained or has lost based on the band that we use. And so I'm going to go through the workflow of this process. And so for the data collection process, this figure here, these purple areas show where we will be collecting our data. And as I said earlier, we'll be focusing on the wetland areas. One, because of the ecosystem services, but also because they are also extremely hard to map. Forested wetlands and shrub-scrub wetlands look exactly the same as an upland forest area, and so just using multispectral imagery or vegetation indices isn't really enough to get an accurate classification, and I'll go into that a little bit more in a second. But I'll also be using Sentinel-2 multispectral instrument imagery and Sentinel-1 synthetic aperture radar imagery to get our multispectral bands and vegetation indices and our radar imagery to get the texture of the area and use these as variables for our data set. I'll also be using a depth to water table data set as a variable as well. And I'll be using the NOAA and USGS quality level 1 LiDAR data set to derive digital elevation models, or a digital elevation model, canopy height model, and slope to use as our variables as well. And we'll be setting a threshold for the canopy height model at 6 meters for forested wetlands, because the National Wetland Inventory has defined a forested wetland as above 6 meters, and anything below 6 meters that has woody vegetation is a shrub-scrub wetland. And this is the variable that we are able to use to really hone in on these areas and accurately classify these areas. And so this is just a table of all the variables that we're using. They're separated into topographic, texture, and vegetation. I really just want to point out the synthetic aperture radar. This really allows us to tell the borders, or be able to define where borders are, so areas between cropland and forested areas, and also areas where there is a lot of water in the area, which is also very important for classifying wetlands because there's a lot of water in those areas. So to continue, once we have the classified training data set, we'll do initial modeling, and we are using classification and regression trees, support vector machine, random forest, and gradient boost. And out of those 4 models, we are going to pick the best one to use for our final land cover classification. And we'll do variable selection, hyperparameter tuning until we get the best overall accuracy so we can get our finalized model. And currently right now, our best model is the gradient boost model, where you can see the overall accuracy is around 85%. The producer's accuracy is around 86%, and the consumer's accuracy is around 87%. And this figure over here just shows the variable importance. I don't know if you can really see the variables, but the top 4 are the 2 radar bands that we're using, and the canopy height model and the digital elevation model. So it's good that we're seeing that they're the most important. And for the producer's accuracy and the consumer's accuracy, the producer's accuracy is basically the point of view of the map maker. So this is how often real features on the ground are correctly shown on the classified map, or the probability that a certain land cover of an area is classified as such. And so the consumer's accuracy, or also known as user's accuracy or reliability, is the accuracy from the point of view of the user. That's why it's called the user's accuracy. And it essentially tells us how often the class on the map will actually be present on the ground. And so for any given class, these will not be the same. And you can look at the upland forest class, for example, where with the producer's accuracy is around 78% and the consumer's accuracy is around 63%. This means that even though 78% of the reference upland forest areas have been correctly identified as upland forest, only 63% of the areas identified as upland forest in the classification are actually upland forest. And so we can look at that for all our classes here. And now I'll continue. And so this is the vegetation condition part of the workflow, where we will be using annual collections of Landsat imagery for 7 and 8 from 2000 to 2020. And for this, we'll be using Landtrender to get a vegetation loss and a vegetation gain from the Landtrender. And from here, with the magnitude, we can get the overall magnitude of change from 2000 to 2020. And with that, we can perform a principal component analysis where we can take all those bands, all these magnitude bands right here that are stacked together, and through the principal component analysis, we can basically smush them together into a dimensionless one band, and it basically just shows the highest variance of the spectral values, and from that we can get our total loss magnitude and our total gain magnitude, and from that we can do a PC1, which is the band with the most variance, versus our mean analysis. And basically what this shows is how much information has been lost from our principal component analysis. And what we're looking for there is just a high correlation, just to show that we haven't lost that information from doing the PCA. And from there, we can do some additive band math to combine these two figures here to get our final condition index. And so this is the gain PC1 versus mean analysis. And basically all I want you to know is that it has a high correlation, so it basically means that we have not lost that much information for that. And same with the loss, it's a little less so, going from 0.9 to 0.7, but still highly correlated, still what we're looking for. And so these are the two figures from that workflow. So the one on the left here is the vegetation type or land cover, and the one on the right here is the vegetation condition from the Landtrender. And basically, you can see with the vegetation condition, the areas in green are areas with the highest gain, and areas in red are the areas with the highest loss. And I symbolize this through basically 2 to 3 standard deviations away from the mean to show the areas that are experiencing the most significant change within these areas. And you can also see here the land cover classification. And so for the final objective within this project is creating a green infrastructure biophysical suitability index. And so that is a quantitative measure of how suitable an area or location is for a particular use. So in this case, green infrastructure. And so we'll be using topographic variables, again, from the NOAA USGS Quality Level 1 LiDAR dataset, and edaphic variables from the USDAG Sergio database. And from the topographic variables, we can get digital elevation model, slope and flow accumulation. From the edaphic variables, we can get soil texture, percent imperviousness, and hydraulic soil groups. And those will be modified by built environment variables, so proximity to green spaces, where areas are, and for if it's a government-owned or open parcel, distance to main roads, things such as that. And from there, we can get our green infrastructure biophysical suitability index. And then we can combine all 3 of the indexes through a weighted overlay analysis to get our final green infrastructure suitability index. And this project is still ongoing, so we have not done this part yet. We still have to collect more classification data this summer for our second objective. But real quick, what this suitability index can do is basically show where areas are most suitable for green infrastructure. And here are some examples of green infrastructure. So we can implement things such as rain barrels, rain gardens, pervious concrete, reconstructed wetlands. For this project, we are mainly focusing on flood mitigation and adaptation, but it can also be used for other ecosystem services such as like filtering pollution or just overall improved water quality or air quality. And so another example, so this is an area within historic Fourth Ward Park in Atlanta, Georgia. This is a before image of an area that they identified as an area for that was suitable for green infrastructure. And this is in the same area, but after. So you can see how much more beautiful it is, and just, you can't really see the ecosystem services that it provides within this image, but just the societal and health benefits that we can get as humans from areas like this is just very important. And other areas within North Carolina that have done this, or like Raleigh with like the greenways and stuff like that. And so an area within Wilmington that we're starting to implement is things like this is within the Anne McCrary Park. And so this is a bioretention pond that was recently installed. And basically, this is a low-cost way that we can implement green infrastructure to provide to improve our ecosystem and societal resiliency. And so, thank you. Any questions? Yes. Have I made my Earth Engine code public? No, I have not made it public. I've been doing it within the JavaScript API, but I know it can also be done within the Python API too, but no, I have not made it public. Thomas.
You will.
Yes, but I will, yes. Yeah, so let me go back a little bit. So with LandTrender, basically what it does, you give it a start date and an end date, and it goes through every single image within the area that you give it, and it goes pixel by pixel and looks at spectrally how that area has changed. And so you can give it specific bands to look at within it. So like red, near infrared, SWIR 1, SWIR 2, but you can also give it vegetation indices, so like NDVI, NDWI. And through those, it can calculate where areas have either gained in vegetation or lost vegetation based on those spectral values. And it's able to keep track of how long the change was and when the change started, when it ended. Yeah. No. Of course. Yes.
Do you already use Google Earth Engine, or do you have to know coding to use it?
People have created user interfaces for Google Earth Engine.
What was the question?
Do you have to know coding to use Google Earth Engine? People have used Google Earth Engine or have created user interfaces for Google Earth Engine, so you don't have to use coding. So like with LandTrender, it was a user interface that I could use, so it made it a lot easier. But yes, you do need to know a little bit of coding to use Google Earth Engine. But I do have to say, with Google Earth Engine, the documentation of everything is, there's a lot out there. And if somebody has had the same problem as you could probably find it. And I do want to give a shout out to Dr. Wu from the University of Tennessee. He has a YouTube series, and he has hundreds of videos that go over the JavaScript and Python API of Google Earth Engine, and they're pretty great. So, yes, and yeah, and it helped me with my NASA internship a couple summers ago. Yes.
Did you run into any issues with going from the 10-meter Sentinel to the 30-meter Landsat?
Did I run into any issues going from the 10-meter Sentinel to the 30-meter Landsat? No. That's one of the things with Google Earth. Yeah. That's one of the things with Google Earth Engine is when you're kind of exporting the images and you're going through the process, it has that built into it to where it'll do that process for you, and you just basically tell it, hey, I want this at 10 meters instead of 30, and it'll just be like, okay, here you go. So, yeah. Yeah, I mean, it's more on the back end of it. So there's no like actual like coding that you have to write, but yeah.
And
Yes.
the accuracy assessment, was that retained from your training samples, or did you do additional, like, photo interpretation?
It was a mixture. So we have current ground truth samples that we've already collected, but to make the data set a little larger, we did do a visual interpretation of imagery to make that data set larger. But we will eventually, hopefully this summer, go collect more ground truth data to make it a little bit more robust. Yeah. Yes.
What's the resolution of your canopy height?
What's the resolution of my canopy height? The resolution of the canopy height model, I believe, is at 0.5 meter. And yeah, and that's kind of the great thing about the QL1 LiDAR data set, is just how accurate or how fine we can get that spatial resolution to. Any more questions? No? Okay. Thank you.